All right. So here we go in lesson 4. Uh, um, this lesson, this unit, in case you don't know, is all about square roots, right? We've looked at um, we first developed them as an inverse to squared functions, and we worked on graphing them. We saw that they follow the same sort of transformations that we know and love: shift, left, right, up, down, all that. Lesson 3, we looked at solving equations that have square roots, and we learned that we can square both sides to get rid of them. But we encountered a little bit of a problem, and that is when you square both sides of an equation, you can oftentimes introduce extraneous solutions. So, an extraneous solution, what's that? That's right. It's a wrong answer when you didn't do anything wrong. Or, like I said, you've done everything right, but it's still wrong. So that we need to be aware of that. All right, we're going to start by solving example 4.1a. It's already got the radicals as isolated as they can be, so I'm just going to square both sides to get rid of the radicals. And then from here, I'll distribute. And this is just a simple linear algebra equation. So nothing too fancy here. We do need to check our work though, okay? So I'll replace x with 4 and see if they work out to be the same. So this is the square root of negative 1. Well, that's just the square root of 1, and that definitely equals the square root of 1, so we're good. All right, so that wasn't too bad. The next one's going to be a little bit more fun. We want to isolate the radical as best as possible, but I've got 2 radicals over here. Um, so I really can't do that. And when there's 2 radicals, you often end up having to square both sides of the equation twice. So I'm going to do that. Now, on the left-hand side here, I need to expand this out. We need to remember our pattern that when you square a plus b, it's a squared plus 2ab plus b squared. So when I square this, I get 4 times, so the 2 gets squared and the root goes away. So it's 4 times the negative x, which is a negative 4x. Then I have to multiply these 2 together and double it. So it becomes a negative 4 root negative x. Then I square the negative 1. And the other side becomes just x plus 1. Now it's an equation with just one radical, and we need to isolate it and square both sides again. So I'm going to move everything over to the other side except for the part with the radical. And I end up with just a 5x, I think. Now, if I could divide both of these terms by something, I definitely would. But I don't want to cause fractions usually at this moment, so I'm just going to go ahead and square both sides right now. So the negative becomes a positive 16. The square root of negative x, though, becomes negative x. All the square does is cancel that square root. The negative inside it's still there, so it's a negative 16x. And then this is a 25x squared. All right, so now at this moment, that's when you say, okay, this is a quadratic. I've got to set it equal to 0 and hopefully factor. If I can't factor it, I'm using the quadratic formula. And I can factor out an x. And then if I set each factor equal to 0, we get x equals 0. and x equals negative 16 over 25. But we got to check them. You can pretty much immediately rule out one of those two answers. Which one? Which one of these definitely does not work? It's pretty easy to plug in. 0, because you would get negative 1 on this side, and a square root can't equal a negative number, right? At least not of a real number. Negative 1 equals 1 does not work. So that's gone. And I'm going to use some scratch paper, and I know it's kind of ugly, but we need to do it. I mean, if there's one thing you get good at in this class, hopefully it's handling fractions. Negative x makes this a positive 16 over 25. And like this one looks ugly, but it's really not that bad. We just need to square root the top and square root the bottom. So the square root of 16 is 4, and the square root of 25 is 5. Negative 16 plus 1. The 1, we need a common denominator. It's 1 over 1, so I'm going to multiply by 25 over 25. Negative 16 25ths plus 25 25ths is 9 25ths. And so its square root becomes 3 over 5. When you multiply 2 times 4 fifths, you get 8 fifths. I need a common denominator. That's 1 over 1. I'll multiply top and bottom by 5. 8 fifths minus 5 fifths is 3 fifths. So we got one right answer. Okay. All right, we saw that this does not just apply to square root functions. We can also use cubing to get rid of cube root functions. So on this next problem, let's cube both sides. So the cube root, this is called the index of the radical, right? We could have any number there. If there's not a number there, the index is 2. So the cube root and cubing will cancel out, leaving me with just x squared plus x. And then over here I get x cubed. So this is a polynomial. We're going back now to unit 8. We know that just like quadratics, we set our polynomials equal to 0, and we factor. And we hope we can factor easily. If we can't factor, we got to do synthetic division and guess and test things and all that garbage. So I get x cubed minus x squared minus x. Now I'll factor out an x. And then I'll factor this. And I get x minus... Oh, does that not factor? Oh my goodness. Well, I was able to factor out an x. That's not bad, right? So we're going to have to just set each equal to 0 and go from there. So x equals opposite b plus or minus the square root b squared minus 4ac all over 2a. So 1 plus 4 is 5. So our solutions are x equals 0, x equals 1 plus the square root of 5 over 2, and x equals 1 minus the square root of 5 over 2. If this was a square root equation, I would have to check these answers, and that would require a calculator. But it's not a square root equation. It's a cube root equation. And cube and cube root are perfect inverses. So they completely cancel each other out perfectly. They're not going to cause extraneous solutions. So I'm just going to trust I did my math right, because there's not going to be an extraneous solution. And there we have it. Okay, so I've got 2 problems for you to enjoy the thrill of mathematics with. Oh, look at C. Looks like you get to divide by possible rational zeros. I'm excited to see how you handle that. Let's do it. Okay, let's see how we did. Um, square root is already isolated on A. We just simply need to square both sides. And of course, if you know your squaring binomial pattern, then this makes it a little easier. If you don't, you're over here doing this. Okay? Foiling that out. So this just directly cancels, gives me x squared minus 3x. And when we square this, you square the first term, multiply the two together and double it, and square the last term. It's a polynomial, so I'm thinking, okay, I need to get it equal to 0. But you'll note that when I try and get the x squareds on the same side, they just go away. So it's actually going to be just a linear equation. Subtract the 2x over, and you get x is equal to a negative 1/5. So to check this, it might be a little bit challenging here. Let's see what happens. Negative 1/5 squared becomes a positive 1/5, and then this negative 3 times the negative 1/5 becomes a positive 3/5. So this is the square root of 1/5 plus 3/5, which is the square root of 4/5, which is 2 divided by the square root of 5. Now, we're not supposed to leave radicals in the denominator just because people say not to. There's really no other reason. But this is us. This is just our work. We're just checking, right? So it's okay to leave it there, is what I would say, right? I've done this wrong. I realize I have made a big mistake. Because I squared the 1, I did not square the 5 down here. Which means I don't have a common denominator. My mistake. I need to multiply by 5 and 5 on the bottom. I got all excited when I saw the two 5s. So I was like, oh, yay, I don't have to get a common denominator, but I do. Oh, and that's good. It's actually going to make my life a lot easier. Look at that. I got square root of 16 over 25. That's just 4/5. All right. Then on the other one, I got x plus 1. So that's what? Negative 1/5 plus 1. Ah, that's just 4/5 as well. So it works. Negative 1/5. All right. Let's do letter B. I've got square roots on both sides. I can't really get any prettier than that. I need to just go ahead and square both sides right now. And when I do that, the right side's easy. It's just a negative 3x. The squaring doesn't get rid of the negative inside the radical. It just cancels the radical. And on the inside here, I need to FOIL that. Be really careful here, okay? Don't call this x plus 7 plus 1. That's not true. You have to expand this out. So when we square a binomial, first you square the first part. That's the a squared. That gets rid of the radical, x plus 7. Then I need to multiply these two together and double it. So 1 times x root 7, 1 times root x plus 7 is just 1 root x plus 7. Now I double it, and I get 2 root x plus 7. Then I square that, and I get a 1. All right, let's isolate the radical. And I get negative 4x minus 7. No. Minus 8. 7 plus 1 is 8, all right? And it looks like I can actually go ahead and divide everything by 2 safely, so I will. Okay. Now I'll square both sides again. I get x plus 7 equals 4x squared. Then multiply these two together and double it. That'll be a positive 16x. And then square the negative 4 to get plus 16. All right, now we set it equal to 0. I have 4x squared plus 15x plus 9. And but believe it or not, I believe this actually factors, right? Because I can do 4x plus 3 and x plus 3. That's 12x plus 3x is 15x, right? So my solutions, if you allow me to do a little bit of work in my head, is negative 3/4 and negative 3. The negative 3 is easy to confirm that that's true. The negative 3/4, well, we need to work on that one. So does everyone agree on that one? Yeah. But this other one, okay, we'll go ahead and do that. The square root of negative 3/4 plus 7 plus 1, does that equal negative 3 times negative 3/4 square rooted? So 7 over 1 multiplied by 4 over 4. That 28 minus 3 is 25. So this ends up being 5 over 2 plus 1, which is 2 over 2, so 7/2. And this is, what, 9/4? Whoops. That didn't work. So negative 3 is the only solution. Unless I made a mistake on my check, but I don't think I did. Did y'all see anything wrong with that? Looks okay to me. That's the wrong one. That's the right one. Yeah, that wasn't the right one. I was confused where that came from. That was the old problem. Yeah. Yep. Okay. Letter C. Okay. Ooh, we get to cube both sides. Okay, that's more fun. So when we cube this, I don't know if you remember your Pascal's triangle business. That would help, actually. If not, you're just going to have to multiply that out 3 times. But it's 1x cubed plus 1 times x squared times 2. I'm sorry, 3 times x squared times 2. So it's actually a 6. 1, 3, 3, 1 is the pattern. Then 3 times x times 2 squared, so 12x, and then plus 8. So 0 equals x cubed plus 5x squared plus 12x plus 8. The possible rational zeros here are 1, 2, 4, and 8, but it could also be negative. So let's synthetic divide. I always like to start with 1 or negative 1, so let's try 1. I got a bad feeling about this. All right, I'm going to stop right there. Let's try negative 1. I have a good feeling about this. Huzzah! So that means that this must factor as x plus 1, because negative 1 was a 0. X squared plus 4x plus 8. And I can use the quadratic formula on that one, but it's going to be no real solutions. So negative 1 is the only answer. It is not. It does kind of look like the sum or difference of 2 cubes is the one that always ends up with a quadratic. There's no real solutions. I simply did the discriminant real quick in my head. Remember, the discriminant is the part underneath the radical. And so in this case, it becomes 16 minus 4 times 8. That's a negative 16. So it's an imaginary square root. Okay. We've done these a lot. I think we've been finding the domain of stuff since like Unit 2. But it's just so important, and I know that it's challenging. So let's review it. In this class, our domain is the set of all real numbers that give us a real number for y. So we're gonna start with all of our x values being all the real numbers, but we're gonna have to remove from that set all the numbers that give us a non-real y, because we're only graphing in the real numbers. So f of x, the y value here, will be a real number as long as the part underneath the square root is not negative. As soon as this thing under the radical, the 15 minus 3x, as soon as it's negative, we've got imaginary numbers. So my domain requires that 15 minus 3x be greater than or equal to 0. This is not a difficult inequality to solve. It's a linear inequality. I just need to remember to flip the direction of the alligator when I divide by a negative number. So this says x is less than or equal to 5. So my domain is negative infinity to 5. That's a parenthesis because you can't actually reach negative infinity. Okay, not too bad on that one. Let's take a look at letter B. Cube root. I can odd root any real number. There, it's the cube root of negative 8 is asking what number times itself 3 times is negative 8. Well, negative 2 times negative 2 times negative 2. Right? So because when you cube a negative number, it's still negative because it's an odd power. So this has a domain of all real numbers. So you can say all real numbers are just negative infinity to infinity. It has no problems at all. Remember, the things we can't do are divide by 0 or take a square root or, more generally, any even root of a negative number. So 4th root, 6th roots, all those things. All right, on letter C, again, we have a square root. We know that our domain requires that the part under the radical end up being not negative. So x squared minus x minus 20 has to be greater than or equal to 0. And I can factor this. And when we solve inequalities with polynomials, right? Non-linear inequalities, the only way we can do this really is to draw a number line and test our regions. So we have it equal to 0, and then we draw a number line. And my critical numbers are the zeros, 5 and negative 4. So at those values of x, if I plug in negative 4 here or 5 here, I will get zeros. Since we can square root 0, it's greater than or equal to 0, I'm going to include those in my set. So I'm going to color in those endpoints. And then I'll test these regions. So this region in the middle here, I can easily test it with a number between negative 4 and 5, like 0. If you plug in 0, you'll clearly get a negative value there. I usually do the factored version. But the original is also just as easy in this case. Bigger numbers I like to factor. For example, let's pick a number to the right, like 8. I'm going to pick a number over here. 8 minus 5 is 3, and 8 plus 4 is 12. I don't care what that is. That's not that hard, but I don't care. I just need to care if it's positive or negative. You know, if I plug in a number bigger than 5, any number bigger than 5 is going to be positive in this factor, positive in that factor, 2 positives multiplied to a positive. So it's positive everywhere over here. And we're allowed to square root positive numbers. Now, if I try a number to the left of negative 4, like negative 10, I end up with a negative in both places, but 2 negatives multiply to a positive as well. Another way to have solved this inequality, you might have thought, hey, I know the shape of this graph. That's a parabola with a leading coefficient that's positive, so it opens upwards like this. And so in this region, we're above the x-axis. Here we're below, there we're above. So our domain is negative infinity to negative 4. We're going to include the negative 4. And then we're going to union that with 5 to positive infinity. All right, next let's look at letter D. This one's kind of combining a couple of problems. We can't divide by 0, and we can't square root a negative. Usually, the part under the radical can equal 0, because I can square root 0, but the square root of 0 is 0. And I can't divide by 0. So, because of that, extra restriction with the radical being at the bottom, I need to require that 9 minus x squared be strictly greater than 0. I can't, usually when you have a radical, I would say greater than or equal to, but because it's in the denominator, it can't equal 0. So I will go from there and we'll factor this as well. It's a difference of 2 squares. Got zeros at negative 3 and positive 3. And again, we could use our knowledge of the parabola shape to really help us. Think of this as the x-axis, okay? We know that this graph, we're graphing, if we look at the graph of 9 minus x squared, we just found zeros at negative 3 and 3. But because the x squared is negative, it's opening downward. So instead of, like we had before, this time the part that's above the x-axis, the y value, 9 minus x squared, is positive in between those two places. So it's actually positive just right there. And the other places it's negative. So our domain here is the open interval from negative 3 to 3. All right, looks like we got some more practice problems to experiment with. I'm going to ask you to do A, B, and C. And we'll go over those. All right, let's just see how we did. Okay, so we start with this one. It says f of x equals the cube root of x squared minus 1. I can cube root any real number. I don't have to have that restriction that I do for even roots, because the cube root of a negative number is a real number. So there's nothing to be concerned about. The things we need to check for are even roots and dividing by 0. So this is fine. The domain is all real numbers. Or negative infinity to infinity, either way. All right, but this here, then I do have something to worry about because I got a square root, not a cube root. So I'm going to say that my domain requires that whatever x values I use, they have to make x squared minus 4 greater than or equal to 0. So I'll draw a number line. Negative 2 is the 0 there, and positive 2. So that's where they're exactly 0. Those are okay. If I check the regions here, I could do that, check each one, or I could think about the shape of this graph. Let's check the regions. If I try x equals 0, 0 squared minus 4 is a negative number. And if I try something like 4, 16 minus 4 is definitely a positive number. If I try a negative number like negative 4, it'll still be 16 minus 4. So what we're saying here is x squared minus 4 is negative only in between these two numbers here. And I can't square root those numbers, so they can't appear on my graph. Because remember, our domain is numbers such that they're real numbers in, real numbers out. That's what we require. We require real numbers to go into the function. They give me a real number coming out. If they don't give me a real number coming out, I got to throw them out, right? So my domain is negative infinity to negative 2 with a bracket union 2 to infinity. And, just to reinforce that, let's take a look at the graph of that. That's the square root of x squared minus 4, I think. And you can see that everything's fine over here. The graph is appearing wonderful. We're getting some nice numbers, but right in between here, nothing. Nothing in between negative 2 and 2. There's no number. No matter how much I zoom out, because the function is not defined there since it's a function of real numbers. Okay? All right. Letter C. Okay, I got a square root. I'm not allowed to square root a negative, right? So my domain says x squared plus 1's got to be greater than or equal to 0. This function never does go negative, though. X squared is always a positive number for real number x's. Plus 1. So you're talking about a 0 or positive plus 1. That's always positive. So, or if you try and find the zeros of this, you'll get that it's I. right? It's a plus or minus I. In other words, this never equals 0. It's always positive. My domain is negative infinity to infinity. So just because I have a square root doesn't mean I'm going to have a domain that's restricted. It still might be negative infinity to infinity. It depends if what's under the square root will ever go negative. In that case, it never does. All right, we're going to kind of round things out here by practicing a little bit of simplification of radicals. We've done this before. It's just kind of been a while. We're talking about radicals. It fits in nicely here as well. So let's do that. When we're adding and subtracting radicals, they have to have the exact same radicand. They have to have the exact same index. So we need that. It can't do square root with cube root. It's got to be a square root and a square root. And it's got to be exactly the same thing here as here. That being said, sometimes we can get lucky and we can actually do some simplification and make them the same. So in this first example, the only things I can combine are the 4 root x and the 5 root x, making 9 root x, and I can't really do anything over here. All right, letter B, simplifying with just numbers. I don't have any like terms, right? They're all square roots, but I don't have the same thing under the radical. But we might be able to work some magic here. So let's work with the 12 first. The number 12, 4 times 3, which is 2 and 2, is 2 root 3. The number 8 is 4 times 2, which is 2 times 2, is 2 root 2. The number 27 I can reduce as 9 times 3, which is 3 root 3. Now that I've simplified them down, and that's why one of the reasons why that's a good skill to have. If you can simplify the radical down, then you can get them all kind of in these common terms that you can then combine as if possible. So I actually have 2 root 3 minus 3 root 3 is a negative 1 root 3. 3 root 2 plus 2 root 2 is a 5 root 2. Okay, on letter C. Hopefully someone remembers how to do this. Anybody got an idea? If this was just 6 over root 3, I would multiply by root 3 over root 3. I got to multiply by the conjugate. Same thing we saw when this was an imaginary number. I have to multiply by 2 plus root 3. So I'm changing the sign in the middle. Was a minus, now it's a plus. So then this becomes 12 plus 6 root 3 over, I got to expand all this out. 2 times 2 is 4. 2 times root 3 is 2 root 3. You may be wondering why I'm doing this entire thing times this. The division symbol here is actually a grouping symbol. There's actually parentheses there. I just don't have to write them. Okay, so we had 4 and then plus 2 root 3. And then I got a negative root 3 times 2. That's a negative 2 root 3. And then a negative root 3 times a positive root 3 is a negative 3. Because the roots cancel out. All right, those go away. And I'm left with 12 plus 6 root 3 over 1. So that's my solution. 12 plus 6 root 3. Well, long story short, they cancel out because I picked them that way. When you multiply 2 conjugates, that's always going to happen. So because they are opposite signs, I got a positive 2 root 3 and a negative 2 root 3, so they go away. And then the root 3 and the root 3 becomes positive 3. Is that good? All right, let's take a look at letter D. Hint, one of these will need an absolute value. Let's talk about why. First, we're going to simplify this expression. When you've got numbers inside it, it's pretty simple procedure here. You just, make your factor tree. For every pair, you can bring out 1 outside of the square root. So I can pull out a 2. But now I got to think about what is the square root of x to the 4th. Square root, and we're gonna learn this and study this in more detail, is really an exponent. It's an exponent of 1/2. So when you have square root, you just want to divide the exponent by 2. Another way of thinking about that is that x to the 4th is x squared times x squared, so it's a pair of x squareds. And we know if you have a pair, I can bring one out. So I'm going to bring out the x squared. Okay? All right, now let's talk about the y to the 6th. The square root of y to the 6th is going to be y to the 3rd. Because I get to just divide the 6 by 2 because, I'm bringing out pairs. This answer is like 90% right. It's so close to right, but it's actually not 100% correct. If I told you that x and y were positive values, then it'd be correct. But the truth of the matter is that I need absolute values to make this correct around the y cubed. Let me tell you why. If I plug a negative number in, the whole idea of simplifying is that I can use this simpler expression to get the same result than doing this more complicated one, right? We simplify stuff to make our life easier, but we don't want to simplify and start getting different answers, right? So let's say I let x equal 1 and y equal -1. If I plug that in the original equation, I would end up with 12 times 1, and a -1 to the 6th is a positive 1, so I would get the square root of 12. Oh, I'm just realizing that I never wrote my radical. Remember we had a pair of 2's, we forgot about the 3. Still need that there. That's not going away. Sorry about that. And 12, of course, is 2 root 3. But if I plug in a -1 to this expression without the absolute value, I would get 2 times 1 times -1 cubed is still negative. And so I would end up with a -2 root 3, which is not right. Just to try that one more time to explain. This is the problem. That's only true if y is always positive. Because if I put a negative number in for y here, the 6th power first, I put it to the 6th power first, right? That 6th power makes it positive. And so I need to realize that because cubing something could keep it negative, I need to ensure that it's always positive. And just in general, this here, you really want to know that's the absolute value of y. You want to know that. An Algebra 2 student should know that. That the square root of x squared or the square root of y squared is not y. It's the absolute value of y. All right, so anyway, I digress, of course. So that is the correct answer, using absolute value there. The general rule of thumb is if it's even power in and an odd power out, you need absolute values. Even in, odd out, absolute value. Okay? All right, let's take a look at this next one. It's cube root. So the cube root of 8 is a perfect cube root. It's 2. If it weren't, I'd be over here making a factor tree and pulling out groups of 3. The cube root of x cubed is just x. And the cube root of y to the 6th is simply y to the 2nd. 6 divided by 3. The cube root cancels that down. All right, so what I want you to do is to finish off these practice problems for these, and I'll leave those to you.